All right, so today's video is focusing on simplifying radicals. This whole unit is on radicals, like we learned about the key features of them last video. This video is going to be focused on more of the algebraic side. So we're going to learn about cube and square radicals, so it's important that we understand the different parts of a radical. So this is what we call the index. And that just is a number that changes. So if there's no number there, then we assume it's a 2. But if it's a 3, that means we're looking for the cube root. If it's a 4, we're looking for the 4th root. And then for some reason, we have a hard time remembering what this symbol is called, but it just is called a radical symbol. And then the number that's underneath the radical symbol, or like in the house, some people call it, is the radicand. The radicand number. So here we're going to list off some perfect squares because it's going to be important that we know the perfect squares in order to simplify radicals. So the first one, 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. And we're just going to continue that pattern. So 4 squared, 16. 5 squared, 25, 6 squared, 36, 7 squared, 49, 8 squared, 64, 9 squared, 81, 10 squared, 100. So this is a helpful list that you can always look back on, or you can just make a quick list at the top of your paper if you're working on a problem. But it's really helpful to have these handy. And then when it comes to simplifying non-perfect square roots, right, because we can find the square root of 16 really easily. We know that that's just 4. But there's kind of 3 steps. So the first step is to find the largest perfect square that multiplies into the radicand. Okay, so that's the first thing. The second thing we do is we take the square root of that perfect square we found, and we move it outside the radicand. And then lastly, we're going to leave the leftover under the radical symbol. So for these ones, it'll be really good to have a calculator or Desmos Scientific Calculator handy, because we'll need to do a lot of multiplication and division that we're not normally used to. So we are going to look at some examples here. The first example we have is square root of 32. So I want to start by finding what is the biggest perfect square that goes into 32. So I think 4 might go into it. So I'll do 32 divided by 4. And that gives me 8. So it works, but I'm not sure it's the biggest perfect square. So now I'll try maybe 16. That's a multiple of 4. So 32 divided by 16. And sure enough, that gives me 2. So 16 times 2 is 32. So I found the largest perfect square. Then I want to take the square root of the perfect square and remove it from the radicand. So under that symbol, I'm going to move out the square root of 16, which is 4. And then I leave the 2 underneath the radical because there's no perfect square that gets us to 2. So I can't take the perfect square of that without getting a decimal. And that's it. That's my whole answer. That's the radical in the most simplified form. So we're going to do the same process with 180. So looking for the biggest perfect square that goes into 180. Again, maybe not, or maybe 4 will work. So 180 divided by 4, 45. That's still a pretty big number, so there's probably a bigger one. 180, not 181. 180 divided by 9. Okay, 20. There might still be a bigger one. 180 divided by 16. Oh, and that's a decimal. I don't want a decimal. So we'll try one last one. 180 divided by 36. Perfect. 180 divided by 36 is 5. So the biggest square root that goes into 180 is 36. I'm going to take the square root of my perfect square, bring that outside my radicand, and then the 5 is my leftover, so it stays underneath. Okay, same thing with 147. So I'm looking for 2 numbers that multiply to give me 147, where 1's a perfect square. So let's try 147 divided by 9. Nope, not that one. Maybe let's try like an odd one, because I don't think it's like 16 or 25. So let's try 49. So 147 divided by 49. Perfect. That's 3. So 49 times 3. I take the square root of 49, which is 7, and then square root 3. Perfect. My leftover always stays underneath. So let's look at the 175. If you feel like you want to try this on your own, go ahead and pause the video and try it, and then you can come back and check actually the next 3 with me, probably 4, 5, and 6 if you're getting the hang of it. But if we look at 175, 2 numbers that multiply into 175, we'll do 175 divided by 25, and we get 7. Whenever the number ends in a 5, it's always a good idea to divide by 25 and see if that works first. It's probably going to be your best option. Oops, I don't need that last square root. So square root of 25 is 5. That goes outside my radical. And then 7 stays as my radicand. Okay, do it again with 48. So 2 numbers that multiply to 48. I think 4 goes in there, and it does, but it still leaves me with 12, so I want to see if there's a bigger one that goes into it. So 48 divided by 16 gives me 3. Perfect. So I take the square root of 16, which is 4, leave 3 underneath the radical as my radicand, and I have 4 square root 3. Okay, so now I look at 45. I know that 9 is divisible by 45, or 45 is divisible by 9. So 45 divided by 9 is 5. So 9 and 5. Square root of 9 is 3. And then radicand of 5 as my leftover. Perfect. So if you tried those on your own, hopefully you had some success, or if you got a little stuck, then you saw kind of what the explanation is, but we're using the same pattern every time, even if our numbers are a little different. So the only thing that's different about these in 6, 7, and, well, it should be, I wrote 2 6s, so in 7, 8, and 9, is that this 2 is our coefficient. So whenever we break down that 45, we are going to end up multiplying whatever's on the outside by 2. So this still doesn't change anything, so I'm just going to have 2 on the outside. And then bring down the 2 things that multiply into 54. So let's figure out what the biggest perfect square is that goes into 54. So let's do 54. Let's try by 4. Gives me a decimal. 54 divided by 9 is 6. So I'm wanting to do, let me give myself a little more room here. So 9 times 6, square root of 9 is 3. So I would have 2, and then 3 square root 6. So I'm just multiplying the coefficient in that number that's in front. So 2 times 3 is 6. So it'd be 6 and square root 6. We'll do another one like that. So we have 28 here. Biggest perfect square that I see that goes into 28 is 4, but let's double check. 28 divided by 4 is 7. Perfect. So 4, 7. Take the square root of 4, which is 2. So we have negative 3 times 2, square root 7. Negative 3 times 2, negative 6, square root 7. So we never multiply that coefficient by the radicand number, just by the number that's outside the radicand, that perfect square that we pulled out. And we'll do it again in number 9. So 150, I think that 25 probably goes into 150. So 150 divided by 25 is 6. So I want to do the square root of 25. And then I have a 6 left over. So negative 5 times 5 square root 6. Negative 5 times 5, negative 25 square root 6. Perfect. So that's a look at how we simplify non-perfect square roots. And the nice thing is that simplifying non-perfect cubes is exactly the same, except for we have to use our cube numbers. So let's write ourselves a note that this is the same process as simplifying square roots. So let's go ahead and make a list of our perfect cube numbers because we'll need to know those. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed, 64, 5 cubed, 125, 6 cubed, 216, 7 cubed, 343, 8 cubed, 512, 9 cubed, 729, and 10 cubed is 1,000. Again, you could always find these in Desmos, and I'll show you how. So if I just wanted to find, maybe for like 6 cubed, that's a weird one. So you just do 6 and then hit this little number to make an exponent, and so the third power would give you 216. One thing that is important to remember about cubes is that you can take the cube root of a negative number. That's the only difference with squares. And it won't give you an imaginary number. All right, so let's look at number 10. So the cubed root of 40. So we are going to look for the perfect cube that would divide into 40. And our numbers get really big really fast, so we don't have as many options. So I'm going to check 8. So 40 divided by 8 would be 5. So 8 times 5 is 40. Take the cube root of 8, which is 2. So 2 cube root of 5. And that's it. So same thing, we just are doing cube numbers instead of squared numbers. So let's look at 192 next. So for 192, I'm not super sure what numbers go into it, so I'm going to start with just trying 27. So 192 divided by 27 gives me a decimal, so not that one. And then we'll try 64. 192 divided by 64 would be, oh, that's just 6, would be 3. So perfect. Let's go ahead and break that one up. So we have 64 and 3. Take the cube root of 64, cube root of 3. So 4 is the cube root that we pull out. And then 3 is the number that we leave under the radicand. So 4 cube root 3. All right, so next one is 432. So 432 is kind of big, so I'm going to start with a bigger number. So 432 divided by 216 would be 2. And this is one where, again, we have that coefficient in front. So we're going to break down 432 and then multiply. So 216 times 2. You do the cube root of 216, which is 6. So then we end up with 2 times 6, cube root 2. 2 times 6 is 12, so 12 cube root 2. Okay. And then, all right, this is our first negative that we've seen underneath the cube root, but it doesn't really change a whole lot for us. So let's look at this one. So if I have a negative 96 divided by, let's try 8, I get 12, or negative 12. So whenever I take the cube root of a negative number, I want the number that's a perfect cube to be negative. Because when I take the cube root of negative 2, and I can show you on Desmos, so if we're going to do the cube root of negative 8, that's going to give me negative 2. Because we're multiplying 3 times, it doesn't give me an imaginary number. So I get negative 2 cube root 12. And in 14, we have another one with a coefficient. So let's go ahead and break up 181, or 189. So 189 divided by, we'll try 27. Oh, and that one worked for us, is 7. So 27 times 7. Take the cube root of 27, which is 3. So we have negative 3 out front, times 3, cube root 7. Negative 3 times 3 is negative 9. And cube root 7. And then one more negative underneath the radical to practice. So again, we want to take out the cube root as the negative. The perfect cube is the negative. So 250 divided by 125 is 2. So negative 125 and 2. We take the cube root. So negative 2 times negative 5 cube root 2. Negative times a negative gives us a positive outside. So 10 cube root 2. Okay, so last thing is I'm going to show you an example of what it looks like to take a cube root with a variable. We might see this a ton, but this is not really what we're going to focus on. We more need the algebraic, but I want you to be exposed to it. So anytime that we're taking a square root and we have a variable underneath, it's like we're doing so the radicand, and then m divided by 2. Because of that invisible 2 that's on the index. So with a cube root, we have the radicand, and then to the exponent divided by 3. Because again, 3 is the index, and it becomes whatever we divide by our fraction. So when we do that here, we are just going to take the square root of 9. That's a perfect square, so that gives us 3. And then we have k to the 10 divided by 2 because we have that invisible 2 as our index. 10 divided by 2 is 5. So we can simplify that to 3k to the 5th. Yep. And then again in 17, we see that 25 is a perfect square. So I have 5. And then 6 is an even number. So I have x 6 over 2. But then we need to figure out why. Because if I did 13 divided by 2, that would give me 6.5, which I can't use a decimal in an exponent. So whenever that happens, I take the whole number, so the 6, and it'd be like y to the 6th power, and then I have 1 y left over. That 0.5 means that there was 1 y that couldn't fit into my perfect square. So I have 5x to the 3rd, y to the 6th, and then 1y still as my radicand. And same thing with this cube root. So I still have a 2 on the outside. And 40 is not a perfect cube, so I need to break it up. Earlier we saw that I think 8 went in, but we'll double check. 40 divided by 8 is 5. So the cube root of 8 is 2. So we have 2. And then 16 divided by 3 here is 5.33333. So that's not what I'm going to use as my exponent. But that does mean that I'm going to take out 5 w's. And 3 times 5 is 15. So that means I would have 1 w left over with the 5 in my radicand. Still need to multiply the 2 times 2. So that's going to give me 4. So 4w to the 5th power and 5w. So, like I said, we're going to mainly focus on algebraically simplifying radicals, but I did want to show you one with an exponent so that if you saw one, you wouldn't be freaked out. And there's a couple variable ones in your practice. If you're watching this on one of our class days where this is assigned, make sure that you look at the top of the formative to see what your next assignment is.